What we have seen so far in the previous video was doing Monte Carlo integration to estimate the value of a definite integral where we're evaluating it between 0 and 1. Now that's quite limiting, but of course I can change any integral to an equivalent definite integral between 0 and 1 by integration by substitution. So let's say I want to integrate a function g of x with respect to x between 7 and 10. Well, that region of integration starts 7 units further along than I wanted, and it's 3 units as long. It's 3 units long instead of 1. So if I do the change of variable that just says shove everything back by 7 units and divide by 3, so y is x minus 7 on 3, then I can check that my top limit of x equals 10 maps to y equals 1, and my bottom limit of x equals 7 maps to y equals 0. So I hope reasonably straightforward integration by substitutions. My x becomes 3y plus 7, and I need to change the integral dx to an integral dy by multiplying by dx by dy, or dividing by dy by dx. You can think of it either way. So the way I would evaluate that is I would just simply evaluate 3 times g at 3 times a uniform 0, 1 random point plus 7, add those up over n of those, and divide by n. Now those cases we've seen so far are both on a finite domain, but it could be done on an infinite domain as well. So let's say I want to integrate e to the minus x squared over the full real line, minus infinity to infinity. You may recognize this as being related to the normal distribution. That's not totally relevant here. Anyway, so I want to change a variable such that as x tends to minus infinity, y tends to 0, and as x tends to positive infinity, y tends to 1. The point is there is no one answer for this. There's literally an infinite number of correct substitutions. But if, for example, I set y is e to the x over 1 plus e to the x, as x tends to infinity, e to the x over 1 plus e to the x will tend to 1. And similarly, as x tends to minus infinity, e to the minus x will tend to 0. So it'll work at the bottom end as well. Now, there's a whole field of better choices of substitution, ones which will have lower variance and converge quicker. We're not going to go into this in this subject, just to say that there are a number of correct substitutions, and some will be more efficient than others, but we're not concerned with that at the moment. So as an example here, I'm going to use the substitution y is e to the x over 1 plus e to the x to estimate the value of e to the minus x squared integrated over the full real line. So if I've got y of x, I don't want y of x, I want x of y. So if I invert that, then I would get to e to the x is y over 1 minus y, or rather x is the natural logarithm of y over 1 minus y. If I want to differentiate that, dy by dx is just y multiplied by 1 minus y. So then when I substitute all of that in, it's a little bit messy. I've got to replace the x in there with a log of y over 1 minus y. And I've got to replace the integral dx with, well, divide by y over 1 minus y times 1 minus y, sorry. And that integral becomes dy. From there on in, it's just substituting through the uniform points and averaging them. So that part is where the machinery that comes from the weak law of large numbers kicks in. But to get to that point, I admit, is a little bit messy. I haven't offended your eyes with a full screenshot of a spreadsheet doing this. But when I did this and I calculated 100,000 realizations based on 100,000 uniform random points, I got that the integral of e to the minus x squared over the full line was about 1.7729. Well, what should it be in theory? If I take a normal distribution function, then, well, if I set mu is 0, then I'd have this e to the minus x squared over 2 sigma squared. So if I set 2 sigma squared to be 1, i.e. sigma squared to be a half, then effectively what I've got is I'd know that the integral of 1 over the square root of pi, e to the minus x squared, integrated over the full real line, is 1, because any normal density function integrated over all values has to integrate to 1. So what this does tell me is that if 1 over the square root of pi times that integrates to 1, then the integral has to be the square root of pi, which in fact is approximately 1.7725. I was getting 1.7729 off my numerical estimate, which was very good. To conclude, this was a slide which I never had in there previously, but a few students had asked for it. Because there are only 4 cases if we're just looking for not the best change of variable, but an acceptable change of variable. Because the bottom limit of the integral is either finite or it's minus infinity. The top limit is either finite or it's plus infinity. So there's 4 cases: finite to finite, finite to infinite, infinite to finite, or infinite to infinite. So what we've got here is just a table of substitutions for each of the 4 cases. This is not the substitution. Each of these is just one possible valid substitution. So if x is finite at both ends, a to b, then y equals x minus a divided by b minus a. We'll map that to 0 to 1. Inverting that, because I don't want y of x, I want x of y, will give me a plus b minus a times y. And then working out the derivative, dy by dx, I'll get 1 over b minus a. So I'm not going to talk you through each of these, but maybe you can just pause the video at this point and just have a look at these and convince yourself that in each case, the bottom limit, whether that's a finite value a or an infinite value minus infinity, the bottom limit will map to y going to 0, and the top limit, whether that's a finite value b or an infinite large upper limit, as either x equals b or x tends to infinity, then the y limit will tend to 1. So applying each of any of those for the appropriate interval that you've got, and then evaluating the integrand evaluated at a large number of uniform 0, 1 variables and averaging those will give you an estimate of the value of the definite integral by the Monte Carlo method for integrals.